Now we will discuss about the moving coil galvanometer. It is a device used to detect electric currents in circuits. It can be converted into ammeter for measuring currents and into voltmeter to measure potential difference across any part of a circuit. A galvanometer is a very sensitive instrument. It can measure currents of the order of microamperes. So, some changes are to be made to use it as ammeter or voltmeter. You cannot use it as it is for measuring currents or voltages. Now, let us discuss about the construction. It consists of a coil of several turns wound over a non-magnetic frame. So, like aluminum frame or like a bamboo frame. So, is used over which the coil is wound on the frame and is pivoted. So, this is the pivot. It is pivoted so that it can rotate about a vertical axis. Now, a spring is attached to the pivot so that the coil of deflection is brought back to its initial position. So, this is the spring arrangement and this is the coil. Now, this inside the frame over which the coil is wound, an iron cylinder is kept. So, that is the iron cylinder. So, this iron cylinder increases the strength of the magnetic field produced by permanent magnetic poles. So, here this coil along with that iron cylinder is suspended in a uniform radial magnetic field. That magnetic field is produced by two concave magnetic poles. So, these are the magnetic poles. Magnetic poles. So, this is north pole, that is south pole. So, these concave shaped magnetic poles makes the field radial, and this iron cylinder increases the strength of the magnetic field at the center. Now, a needle is attached to the frame so that according to the deflection of the frame over which the coil is wound, the needle moves on the scale. In the galvanometer, the center division shows 0 reading. So, depending upon the direction of the current in the coil, the needle moves either to the left side or right side. Okay. Now, the construction is this. I will show you the actual galvanometer used for measuring DC volt currents, and it is like this. So, you can see that here is the coil wound on a frame, and there is a cylinder. You can see that cylinder also, and these two are permanent magnetic poles, and there is a spring arrangement that also can be seen. Here is the spring, and this is the scale over which the needle can move, and you can see this side also. So, you can see the frame over which the coil is wound, and also you can see the iron cylinder, and the spring also can be seen clearly. Okay. So, that is the construction part of a moving coil galvanometer. Now, the principle is the principle of torque acting on a current loop suspended in a magnetic field. So, we derive this formula for the torque on a current loop in a magnetic field, that is BIM, BIA. So, BIA is the formula which we derived earlier, and of course sin theta is there. Here, the theta is the angle between the magnetic field direction and the normal drawn to the coil, that is the direction is the magnetic moment of the loop acts. So the angle between the magnetic field and the normal drawn to the area vector of the current loop is given here as theta, but in this case it will be perpendicular. Always this angle will be 90 degrees. This magnetic field, which is a radial field, will be always parallel to the coil. This is the coil, let us suppose. The magnetic field for any position of the coil will be parallel because of this radial effect. Therefore, always if you imagine normal to the coil, the magnetic field will be like this. So for any position of the coil, that angle will be 90 degrees, pi by 2. Hence, this becomes always 1. Okay. Suppose if there are, that is for one loop. If there are n number of loops in the coil, then you have to multiply it with n. So where n is number of turns in the coil. So that is the torque produced by the magnetic field in which this current carrying coil is kept. So we can call that as the deflecting torque. Now when the coil rotates, then the spring tries to bring it back due to deflecting torque. That is the restoring torque. That is restoring torque of the spring is given by K times phi, where K is actually a constant for the spring. So this is couple per unit twist. Couple per unit twist. And if phi is the angle by which the coil rotates, if phi is the angle by which the coil rotates, the torque of the couple produced by the spring connected to the coil is given by this. Now, in equilibrium, these two torques must be equal. That is, the deflecting torque is equal to restoring torque. Hence, we can write like this: BIAN is equal to K times phi. That is, the needle will come to a particular position, or the coil comes to a particular position where these two torques are balanced. Hence, we can write BIAN is equal to K times phi. Therefore, current in the coil is given by K by BAN into phi. And this quantity is called as galvanometer constant. Therefore, once you know this quantity, then current can be easily calculated. So, the current in the galvanometer is proportional to the deflection of the coil. Hence, you can calibrate the scale on the galvanometer over which this needle moves suitably, so that it may give directly the reading of the current. And since galvanometer, as I said earlier, is a very sensitive instrument, to convert into a ammeter for measuring current directly, a suitable modification is done, so that, and also the scale is calibrated suitably, so that the needle moving over the scale gives the reading directly. Okay. Now this quantity, that is phi by I, that is the angle by which the coil deflects or rotates by the current. This quantity is called as current sensitivity. Current sensitivity. That means for small current, the deflection of the coil should be large. Then we say it is highly sensitive. It has a large current sensitivity. That is, the angular deflection per unit current is defined as current sensitivity. From this formula, we can write that is 5 by I is equal to BAN by K. So you can increase the current sensitivity of a galvanometer either by increasing the magnetic field. So that is done already using the ferromagnetic material in the form of a cylinder, that is the iron cylinder. And by increasing the number of turns in the coil, you can increase the current sensitivity. And also, if the K value is smaller, that is the spring constant, or I can say the couple per unit twist of the spring is smaller, then also current sensitivity increases. In that way, the sensitivity of a galvanometer for measuring current can be increased. Okay. So next we will discuss about conversion of galvanometer into an ammeter and a voltmeter. Now, conversion of galvanometer into an ammeter. You know very well that ammeter is used for measuring current in amperes. The current measured is expressed in amperes. So, and also you know that ammeter for measuring current should always be connected in series in the circuit, so that each and every electron, that is charge, passes through the meter, it will be counted. And we know the charge flowing per second per unit time is known as electric current. So, therefore, all the charges or the electrons passing through the conductor must pass through the ammeter, then only it gives the current in the circuit. So therefore, always ammeter must be connected in series. So for connecting such a meter, it should have very low resistance. Galvanometer has a coil of several turns, hence it has a large resistance. Therefore, to reduce the resistance of the galvanometer so that it can be connected in series and can be used as an ammeter, it is shunted with a small resistance. We can also, another important point of connecting a small resistance parallel across the galvanometer is to protect the galvanometer. Galvanometer is a sensitive instrument and the coil may get burned due to large currents passing through it, or the needle may get bent due to the large torque produced by the large current. Therefore, to protect the galvanometer from passage of large currents, a small resistance is connected across parallel to the galvanometer. So that is called as shunting the galvanometer. The galvanometer can be represented as a meter and a resistance in series like this. So this is how we represent the galvanometer as a meter with a resistance capital G in series. Now, if you connect a small shunt resistance across this like this. So let us say this is point A, this is point B, and this is shunt resistance. And you know, if a current I passes into the meter connected with a shunt like this, small current will pass through the galvanometer, and large part of the current passes through the shunt. Because we know current through a resistance is inversely proportional to that resistance. The larger the resistance, smaller will be the current. Hence, large part of the current here, the current at this junction will divide into Ig and Is. So, the current through the galvanometer having high resistance will be smaller than the current through the shunt, because shunt resistance is smaller than the galvanometer resistance. So, by applying the junction rule at the junction A, we can write like this: I is equal to Ig plus Is. Okay. Now, across AB, we can measure the potential difference. So, let us suppose VAB. Across this galvanometer resistance, we can use Ohm's law and can be written as like this. Also, the potential difference across the shunt resistance is Is into S. Therefore, these two are equal. Hence, I can write like this. Is into S is equal to Ig into G. Therefore, shunt resistance is given by Ig by Is into G. But we know Is is equal to I minus Ig. Therefore, Ig by I minus Is into G. Take this Ig to the denominator, that is, this is Ig. Take this Ig to the denominator and see what happens. So that is equal to 1 by I by Ig minus 1 into G. So let us represent this ratio as n. Hence it can be written as G into n minus 1. Therefore, shunt resistance can be calculated using this simple formula. So if you know what is the main current that is you are supposed to measure and what is the current that the galvanometer can be used to measure. So if Ig is the current that can be measured with the galvanometer of resistance G, and if I is the current that you are supposed to measure converting the galvanometer into ammeter, then if you know that ratio, that is I by Ig, the current to be measured and the current that can be measured with the galvanometer, and you know the galvanometer resistance, then use this formula to calculate shunt resistance. So in this way, a galvanometer can be converted into ammeter for measuring large currents. So this arrangement is known as ammeter and is connected in series so that the effective resistance is smaller. See, these two are connected in parallel, hence effective resistance will be smaller than the smallest because of parallel connection. Hence, the resistance will be very small, hence it can be used in the circuit in series connection so that the total current through the circuit can be measured. Then conversion of galvanometer into voltmeter. Conversion of galvanometer into voltmeter. That is, a galvanometer, if you connect a large resistance in series, the effective resistance will become large and hence it can be used as voltmeter by connecting parallel across any part of a circuit. So by connecting it parallel, the effective resistance of the combination becomes very small, or the system will not draw any current from the main circuit. Hence, voltmeter should be connected always parallel across any part of a circuit for measuring potential difference so that it will not draw much current from the main part of the circuit. So to have large resistance, a galvanometer, so suppose this is the meter, this is the resistance of the galvanometer, a large resistance is connected in series. So when a current, say suppose I passes through the galvanometer, same current should pass through the resistance capital R also. Then we know that the potential difference between these 2 points A and B is given by Ig into G plus R. So from this formula you can calculate R. Suppose I want to measure with the galvanometer we can measure a voltage of this much. So using the galvanometer you can measure a potential difference of this much. So let us suppose represent it as V suffix G, and the voltage you wanted to measure is say this much, and therefore let us divide one by the other. Then what happens? So I will take this as say V and this is V. So if you divide this equation by this equation, Ig gets cancelled. Then G plus R by G. So that is equal to 1 plus R by G. Suppose if this ratio is taken as n, so n minus 1 into G will be equal to R. So if you take this ratio as N, then N minus 1 is equal to R by G. Bring that G this side, then R will be equal to N minus 1 into G. So the resistance to be connected in series to the galvanometer is given by N minus 1 into G, where N is the ratio of the voltages, that is voltage to be measured by voltage that can be measured using galvanometer. So once you know that, then using this formula you can calculate the resistance that is to be connected in series to the galvanometer, and this whole arrangement can be used as voltmeter and connected across the any part of a circuit in parallel, so that the effective resistance will be smaller and it will not change the resistance of the circuit, so that current or potential difference will not be altered by such a connection. And we can define voltage sensitivity also like this. As we defined current sensitivity of the galvanometer, voltage sensitivity also can be defined like this. So we define this phi by I. So that is equal to BAN by the constant, that is spring constant K. Similarly, we define phi by D, so which is equal to BAN by K. So this is nothing but I by B. This I by B is nothing but 1 by R. So BAN by K into 1 by R. So suppose you want to increase the current sensitivity, you may be increasing the number of turns. So the current sensitivity increases, but the voltage sensitivity doesn't increase, because when you increase this number, the resistance, which is proportional to the length, this is proportional to the length. As you increase the number of turns, length of the coil also increases, and hence resistance also increases by same amount. Therefore, by increasing the current sensitivity, need not always increase voltage sensitivity. From this point of view, I am telling this number of turns point of view. So always it is not true. By increasing current sensitivity, voltage sensitivity may not increase. Okay, so that is about the current sensitivity and the voltage sensitivity of galvanometer. Okay, so with this, the chapter of moving charges and magnetism is completed, and we will go for next chapter. That is, I will be discussing electromagnetic induction in the next class.